Thanks for having me. My name is Arya Subramaniam, and I am a solutions architect at AWS, based out of Toronto, Canada. I work with enterprise customers and helping them build on the cloud and using our technologies to build different solutions within AI, machine learning, as well as now within the generative AI space. And I'm super excited to talk a little bit about how you can use multi-agent systems and how that fits kind of into a gaming context and what the potential is to use that in different use cases. So to just begin, I wanted to briefly go over what we will be covering for today. So first, we'll be discussing what AI agents are, how do you define them, what kind of their capabilities are, and then we'll dive into multi-agent systems, combining multiple different AI agents and how they can collaborate together to achieve some really cool results. And then we'll dive into some live demos of what that might look like in games use cases and what the potential is to use it in different functions within games. And we'll see how one could build that on AWS and finally end with some questions. Okay, so to dive right in, to talk a little bit about the ML space and the game space. Currently, we have traditional ML reinforcement learning being used within the game space, whether that be for building characters or on the production side. And we're slowly seeing generative AI creeping into this industry for creating narratives, building worlds, developing characters and their backstories. But how capable are large language models in their raw states and with the current technologies able to achieve these complex use cases and provide accurate and useful insights? So the first kind of limitation that we're hit with is large language models and hallucinations. So large language models, based on kind of the instructions you would provide it and based on the data that it is trained on, it will try the best based on that data that it has to answer a question and to provide insights based on a task that you want it to complete. But that might lead it to coming up with some inaccurate information or making up some data, resulting in hallucinations, which can be critical to kind of manage when you're using it within the industry and within production systems. The next kind of limitation with using pure LLMs and in their raw state is their limited reasoning capabilities as well. Without providing instructions and specific prompt engineering techniques on how to think about problems or how to go about reasoning for certain problems, maybe with limited tools and capabilities, external data that it might have access to, large language models might not be able to produce the best results and the most accurate results given specific tasks. And finally, large language models do have some trouble dealing with complex processes and flows. And again, one would need to provide some instructions on how those third-party APIs can be called, maybe how retrieval augmented generation can be done to obtain data from vector databases and gain insights from external data sources. And so given all of these challenges, that leads us to kind of AI agents and how it can address some of these problems with large language models. And it essentially gives us a framework to be able to do more complex things and to interact with external systems to be able to achieve those as well. So let's dive into what AI agents are and how we can use them. So touching upon what an AI agent is. So essentially, AI agents are software programs or components that will allow you to use data to perform self-determined tasks to meet some predetermined goals. So you can think of an agent essentially as a kind of a component which has access to some instructions and a prompt which defines its role, its persona, or some task that it needs to create. And on the flip side, it might have access to some actions to interact with third-party APIs, maybe call on some other agents to find some information, or call on certain functions to be able to produce some expected outcomes or even collect data from external knowledge bases. And collectively, this holistic system allows you to better achieve complex tasks and do complex reasoning that you would not be able to do with traditional large language models and a single prompt approach. So let's dive into a brief example of how one could build an AI agent and what this would look like. So over here, I've assumed that maybe I have an NPC shopkeeper bot that I am trying to create, an agent which is an NPC shopkeeper. Initially, I can provide it with some instructions and a prompt based on which it can understand the task at hand or the role or the persona that it's supposed to take on. So over here, I have the instruction of you are a shopkeeper in a medieval fantasy world, and you can only respond as a grumpy old merchant and refuse to break character. So if I was to communicate with this agent, I could maybe ask, how much for this sword? Let's assume the shopkeeper has some swords within its inventory, and you have your shopkeeper bot and the agent responding in character, bah, that rusty old thing, 50 gold coins. And as we continue to communicate with the agent, it will keep in mind the persona, the instructions, and that prompt that was provided to stay in line with the task at hand. So now let's add a little bit of complexity to this agent. We provided an initial instruction, created a persona for this agent that we're creating, the shopkeeper bot. Let's give it access to some tools and some actions that it can use to pull on external databases or do some more complex things. So the first set of tools and actions that we provided with is some inventory actions. So let's assume that we give it the capability to list what the shopkeeper has within its inventory. Maybe this is hooked up to some database on the back end, which has definitions of different items and names, quantities that it'll be able to pull that information from. In these tools definitions and in the actions definitions, you would essentially have the ability to kind of specify what the schema is for making those calls and the arguments, which can be complex to do with traditional large language models and single prompts. And agents give you a way and a framework to essentially create that. And maybe we have another describe item tool as well, where it can gain more information on specific items. And then in terms of some other actions that we have, let's assume that it can take some transaction actions as well and has some transactions-based tools. Maybe you can buy and sell certain products with this NPC shopkeeper agent, and it's able to, once again, interact with those back-end systems that are controlling the different items that you have within your inventory and the quantities as well. So now, if I come in and talk to this agent, I ask, what items do you have in stock? The agent is able to independently kind of understand that we would need to call the list inventory action or the tool to fetch that information from the backend. It's able to execute that tool, gain a response, determine that final answer, and return it back to the user, stating, they've got potions, swords, axes, and bows. And maybe the user wants to buy 2 swords now. So it's able to call on the buy item or the sell item action and to make those changes on the back end in accordance with the capabilities and the tools that it has access to. So let's take a look at agent orchestration under the hood and how this actually works from the agent level. So we have a defined task. This task is being executed by a specific agent. This agent might have access to the prompt, that is the persona, the task at hand, any other instructions for itself, some conversation history from what was previously executed during that session, as well as a list of actions that it can take and some knowledge bases that it can call on, and any other instructions and tasks that it might need. So it will send that to a large language model that would be able to break that task down into distinct steps. And each of those steps then can be executed based on what those steps are by either calling different actions and tooling to interact with third-party systems or to call on knowledge bases to get relevant data using retrieval augmented generation or RAG as well. So once those responses are obtained, depending on the subtasks, those results can be sent back to the agent, who will then send those results back to the large language model to make sure that we're framing the response and the final answer in the format that was expected. Maybe we wanted it in a bullet point format so that large language model and that final invocation would be able to better refine that piece. But let's assume now that you have 100 tools 100 different knowledge bases and some very complex tasks to do. As an agent, you might get super confused and overwhelmed what actions might be most relevant for my task to use at a certain point, what knowledge bases might be most useful for me to call on. And that's where multi-agent systems come into play. So what exactly are multi-agent systems? Essentially, multi-agent systems allow you to define distinct agents with their own specializations and own capabilities and goals. So over here, we have a meeting system example. We might have a scheduler agent, a note-taker agent, translator, data analyst, and each of them have their own knowledge bases, their own tools that they have access to. You might have different large language models that you use for each of these agents as well, based on the specialty and the persona that they are acting upon. And this way, you can create independent entities that can act based on tasks, as well as collaborate with each other to achieve certain things. So let's dive into what the benefits of using multi-agent systems are. So the first is enhanced specialization and expertise by allowing you to better define for each agent, what persona it plays, what tools it might have, and to give it access to resources and information that makes it really good at specific tasks. In terms of flexibility and scalability, you can add new agents on the fly to achieve tasks based on what the requirements are at that point, whereas with a single agent, you might have to change what prompt it has, and that could affect the execution of all of the different subtasks that it was doing. And greater adaptability to dynamic environments with more complex tasks coming in hand. You can kind of pick out and choose what set of agents and what team of agents would be most appropriate to achieve certain goals. So we have some popular frameworks that are being used for multi-agent systems today. LangChain is a popular framework within the generative AI space through which you can define different agents. And specifically, LangChain doesn't allow you to purely define multi-agent systems, and that's where LangGraph comes in, where you would specify different agents as a node within a graph, and the edges would kind of define the connections between those agents. Then we have GripTape, which allows you to define your multi-agent systems as a team, and Crew AI, which is what we will be focusing on today, which allows you to specify different agents with a role, a backstory, a persona, and then to define different tasks and assign each agent to those as a crew. So here's a brief example of how one could implement this in Crew AI, and technically what it would look like in code. So over here we have a simple game code generation example that your game developers could use to fast track getting some initial programming that they need to do. So we would have an agent which we define. So over here we have the example of a code architect agent that is defined with a role, a goal. So over here our goal would be to create Python code using the Pygame package, as well as a backstory which really gives it information on that persona that it needs to take on, as well as kind of the instructions and the context. And you can also provide tools to these agents. For example, we can have a code interpreter tool to allow you to run the code that was generated, and then the large language model, and we'll dive into delegation as well. On the other side, we have tasks definitions. You'd create a task. Over here, we have the example of a coding task. You provide a description of the task, an expected output, and assign that to an agent. And finally, you define all of that as a crew. Define your agents, specify what tasks you want to run as a part of the crew, and then kick it off with any input parameters. So let's take a look at what multi-agent collaboration looks like, and I wanted to concentrate on two specific topics. So the first is kind of sequential, and the second being hierarchical. So for sequential, let's take the example of development of a new software feature. So this is pretty straightforward. So you have your multiple agents. Let's assume agent A, who is a researcher. They're able to take a look at user requirements, do market research, better understand what that landscape is. It sends the output from its task to a second agent, who is the designer, who is able to gather those insights, create wireframes, design prototypes based on the input that was provided by the researcher. The designer will then send that information to the developer to actually implement that in code. and then the developer will be able to pass on the program maybe to the tester who does their own testing, and finally that tester gives those results to a marketer. And so here you can see a standard sequential flow for multi-agent systems, and that's one approach with how to do it, and each subsequent task will take as input the previous task's output. And then a second approach would be a hierarchical approach to multi-agent systems. So over here we have a project management example. So let's assume that we have a project manager. They're kind of at the top of the hierarchy. They're at the highest point in their team, and they have the ability to delegate to different parties within their team. So let's assume that this project manager has access to a design team lead as well as a development team lead, and is able to delegate tasks and subtasks to these different parties, as well as to liaise communication and coordination between them, and call on them for any follow-up questions, or if they feel like certain tasks are not as complete as they need to be, or if they need more enhanced information, they're able to call on these different agents to kind of gain additional information or rerun certain tasks. And then finally, we have our design team leads and the development team leads working with designers and developers. Maybe this is another sequential flow that we would like to create, and then a QA agent and marketing agent making up this holistic system. So we have our top-level agent that manages kind of the system on the highest level, with the highest level of delegation. And then we have our middle-level agents, lower-level agents, as well as support agents. And this is how you could essentially create your multi-agent systems to support different tasks and achieve complex things, and allow agents such as a project manager with management and collaboration capabilities to delegate to different teams, as well as to follow up with them. So we have our managers here, and potentially some function calling agents that have access to maybe code interpreter tools on the side. So I wanted to briefly introduce the GAINS framework, which is generative AI networks. So essentially, this is a framework coming up within the multi-agent space, which talks about using a central coordination agent, similar to that project manager as a management agent, to coordinate a task and to assign certain tasks to different agents. So it might have access to its own tools, its own set of memory. It could have its own persona and instructions as well. And it's able to delegate tasks to different agents. And the goal here really is collaborative problem solving across these. And once it assigns tasks to different agents and gains responses from them and feedback, it's able to follow up and gain clarifications wherever necessary as well. And taking it one step ahead, making these gains even more complex, theoretically, you could have your central coordination agent have the ability to call on a whole separate GAIN network as well, which has its own specialized agents to complete certain tasks. And some central coordination agents could also, create agents on the fly depending on what we would like to achieve. So with that, I would like to dive into the demo to kind of show you how multi-agent systems can be used within some games use cases. So over here, we have a basic example. We just have some foundational examples that will give you the idea of the art of the possible with multi-agent systems. So the first example we'll be taking a look at is creating NPCs. And I'm just going to run this in the backend as well, so it has some time to compute. So essentially, first I will specify a game. So over here, my example is a game called Bloodlines Ascension. It's a vampire first-player shooter game where humans are kind of fighting against vampires, essentially. And we have equipped with us in this crew 4 different agents. So the first is a dialogue generator, second, the character alchemist, an NPC sculptor, as well as an attribute specialist. So let's take a look at what these agents might look like on the back end and how we would define that. So hopping over to the agents page, I can look at the character alchemist. So over here, you can see I've defined a role, a goal for the character alchemist, which is to create unique and memorable NPC personalities, as well as a backstory to provide more context and persona to each of those agents. And then you might be able to supply some tools as well. So I just want to hop on over to the NPC Sculptor, which essentially has access to an image generator tool that uses Stability AI's stable diffusion models on the back end to generate an image of our NPC. So let's head on back over to the mission, which is still computing. But we have our first task, which is for designing that NPC, which is assigned to our character alchemist. And essentially, it's been given instructions to create a character archetype, figure out a role and a playstyle. And such a mission can be used by your game designers to get an idea of what characters might be like, to really come up with some initial sketches for what we want our NPCs to look like and what their personalities and personas could be. Then we also tell it to create some dialogue options for us as well, based on certain parameters: first meeting, combat encounter, offering assistance, potential betrayal, defining attributes, and then finally generating an image. So I can see here that our task has completed. So let's take a look at what we came up with. So over here, this multi-agent system was able to come up with a character, and they essentially are playing the role of the Eternal Inquisitor. And for some dialogue options over here, we have dialogue options that can directly be pulled from the system, and in terms of the way they speak and the way they interact with the main playing characters. So for the first meeting, sticking to its role and kind of the persona we gave it, you reek of the unholy, creature of the night, da 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 da. And if we go on to the attributes piece, it's able to come up with an initial set of physical attributes as well as emotional attributes on some parameters that we set, such as strength, agility, endurance, dexterity, perception. And it's able to give a rating on 1 to 5, which would give a game designer an initial idea of maybe what an NPC could look like, and give them some inspiration to work off of. Let's check out the image it's come up with as well. And over here, taking a look at the character description we came up with on the fly, we have a basic NPC sketch. So that's just for the first use case. Let's hop on over to the next. So the next, and this kind of showcases the breadth of different use cases in which multi-agent systems can be used. So I'm just going to hit run here to give it some time to compute as well. So we have content moderation. And now such a system can be used by any human moderators you might have, or any content moderation recommendation systems that you might use. So for this mission specifically, we've kind of fed it with a transcript of some players. Maybe this is from chat logs or from a voice channel that has been transcribed. And we have player 1 and 3 on the same team, in, again, a first-person shooter game, and player 2 on the second. And as you can see, they're having a little bit of back and forth, a little bit of trash talk. And in terms of the context, the game is in its final minutes, and player 2's team is leading by a narrow margin. And so this is kind of a high-stake game. Emotions could be high, and that will be taken into consideration by these agents as well. So once again, we've defined our agents. We have a content classifier, a context analysis to understand where we're kind of in the game, and then a content moderator. And this time, we are running this task hierarchically, where our content moderator has the ability to delegate different tasks to different agents and kind of control and gain feedback from them as the tasks are occurring. So if we take a look at the first classification task assigned to the content classifier, we ask the content classifier to essentially categorize the different parts in the script based on certain categories, such as harassment, hate speech, threats, explicit content, cheating, discussion, and spam. Then the context analysis kind of takes those findings and better understands how that would fit into the context to assign a severity rating to each of those findings. And then we have a final moderation decision that is coordinated and produced by that content moderator based on the inputs that it sees from the previous tasks as well. And in the interest of time, we can maybe move on to the next use case while it's computing on the back end. And what the content moderator is doing is coordinating with these different agents, seeing if it needs any follow-up questions to ask based on the specific tasks as well. And all of this can kind of be seen in the execution logs of your multi-agent system. Okay, so briefly moving on to the next task. So we have a simple game designer use case. What this would allow you to do is essentially come up with an initial sketch of a basic game and some basic code, which can be used by your game developers to make sure that they're not wasting some time or being more productive when it comes to programming with games. So we have a first game task. So over here, I fed it with an input prompt of snake. I want to create a snake game. Given that description, I first ask it to come up with a complex game prompt. This game prompt essentially will define the specifics of the game. So details on the core game elements, the gameplay mechanics, how the player interacts with the game, as well any scoring system information. And this detailed game prompt is used by this multi-agent system to better define the key components that it is able to program. So the next task is a coding task that it would do that is assigned to a code architect. Then finally, we can do a reviewing task where it will take in that code, check for any errors, any syntax errors, missing imports. And finally, we have a formatting task to make sure that we're kind of cleaning up the code and making sure that we only have the code ready to use. Traditionally, if you were to use a single agent, it might get very confused with not only creating a complex prompt as well as programming this and checking for errors. And so the benefit of using a multi-agent system is really to be able to break these up into specialized tasks that can be handled by single agents. And in fact, you can adapt this further to use large language models that might be fine-tuned on your own code base or that are specific to certain gaming engines that you might use as well. So in the meantime, let's check. It's still taking its time. Let's try and go ahead and run this. So I have a Pygame environment that I have loaded up on the backend. So I'm just going to run the game code that I have over here, and I'm going to try and bring that in here. And I've already lost the game. But let's try but we have an initial snake game that you're able to kind of play. And that really shows the capability of your multi-agent systems to produce something working that can be used by your game designers to make sure that they're not spending too much time on some basic tasks like this, and they're able to employ systems such as these to speed that up. And finally, kind of the use case that I wanted to show is the Gold Rush negotiation. So this is your ability to simulate interactions between different characters. So let's assume that we have 3 different characters, Mayor, Gus, and Cornelius. They exist in a game where it is the Wild West town, and essentially Gus and Cornelius are 2 key figures within this town, and they must negotiate amongst themselves to essentially create this mine and figure out how they're going to split the profits and the ownership. So taking a look at Gus, Cornelius, and the Mayor in more detail, let's see how each of these agents were defined. So first, taking a look at Gus. So Gus has been prospecting this area for years, but he's someone who doesn't really have that capital to invest in developing this mine. So that's kind of the persona and the backstory that he's been provided with. Next, we have Cornelius. Cornelius is a wealthy businessman who has made profit, with many businesses and is really looking for the next best opportunity. And finally, we have the mayor, who has been equipped with those task designation capabilities. So it acts as that management agent, that coordination agent. And essentially, the mayor coordinates and facilitates the negotiation and conversation between Gus and Cornelius. So if we take a look at what it looks like. So the first task, which is assigned to Gus, is to present an offer. So over here, we can see that Gus has come up with an initial expected investment of $25,000 from Cornelius, and he has proposed a profit sharing of 60% and 40% for Cornelius. So then what the management agent or the mayor does is it takes this information, feeds this to Cornelius, asks for feedback, and then asks Cornelius to present his initial offer as well. So Cornelius, sees Gus's offer, reviews it, and based on the context that it has and the persona and kind of that backstory that it comes with, Cornelius presents his counter offer, which is a $50,000 investment with a 50-50 profit sharing between the two. So now the mayor, who is that management agent, is able to take both of these, ask each of them to kind of negotiate back and forth as well, and to see if their needs are met. So it'll coordinate that conversation between the two parties, and finally they're able to reach an agreement. And the mayors essentially reached an agreement with 53% ownership for Gus, 47% for Cornelius, and with an initial investment of $50,000 from Cornelius. And this way you're able to simulate different situations between different characters that are occurring and really see what the art of the possible is and get ideas. And traditionally, if you were to do this yourself, it would take a little bit of time, and you can do this in a matter of minutes with your multi-agent systems. So switching back, I wanted to talk a little bit about what the solutions architecture would look like on AWS and if you were to host this on the Amazon cloud. So the real brain of the application would be in AWS Fargate. Essentially, Fargate allows you to containerize applications, Dockerize them, and then host them in a serverless environment. So that's what would have the Crew AI application with all of the logic. And I've used Fast API as the API endpoint to be able to communicate with this backend system. And this Crew AI application calls on large language models, specifically Claude 3 Sonnet, Anthropic's Claude 3 Sonnet, which is available through Amazon Bedrock, through which you can access a wide variety of different large language models and image generation models. And these are accessed through the front end, which is a React application that has been deployed in AWS Amplify. On the other side, Amplify has the ability for you to essentially call on the other set of APIs to interact with the backend systems and the databases to make sure that the information persists. So we have Amazon API Gateway endpoints, serverless APIs that are backed by AWS Lambda, which is our serverless compute layer that executes some logic to be able to interact with the DynamoDB databases, which is a NoSQL database to kind of store the missions, agents, and tasks information. So diving into kind of how can you add complexity and where do you really go from here, I wanted to talk a little bit about memory for systems and AI agents and how this can be used. So over here, we have different definitions of memory that can be used in a Crew AI application. So you have your short-term memory, which temporarily stores memory from recent interactions, conversation history. Then you have your long-term memory, which is how past executions went and any learnings from those. You have entity memory, which kind of reframes the memory to make it more specific to people, place, and concepts. And then finally, your conceptual memory, which is kind of a combination of all of these to make up an overall context. So for a game space, you can think of this as short-term memory being players' actions, any recent decisions that they've made, any recent levels that they've completed. Your long-term memory could be previous quests, previous levels, and their outcomes, and what a player has been like. Your entity memory would be your game's characters, their locations, items, access to different objects that they might have, other things within the world that they might interact with. And finally, your contextual memory is kind of a combination of all of these, your overall game lore and the holistic world. Another key concept I kind of wanted to bring up was small language models. So till now, we were talking about using large language models for these different agents, but you have the capability to use small language models in multi-agent systems with that ease to swap out the underlying model that is being used. And these have the capability to use lower computation and more specialized to maybe your code base or specific tasks that you would like to do. And this way, you're able to fine-tune based on your specific data, as well as depending on certain engines that you might be using or what that task is. Maybe you want responses in certain formats, you have more control over there, as well as it would be low cost and lower in terms of computation. And so with multi-agent systems, you have a wide variety of use cases. These can be extended even further to touch upon different areas and different teams within the game space, and that make up the holistic games development piece. And so I would encourage you to explore multi-agent systems and these frameworks to help with your productivity. And thank you so much. Feel free to come and approach us to talk a little bit more about how AWS can support you. And it's a pleasure to be here. Thank you.
Fine. Thank you. Really interesting talk. I just had a question if you could speak to your ability to kind of direct agents to stop themselves from endlessly reasoning about a task they've got to do and actually go with it and produce it. Some of my experimentations with agent systems, they often rationalize that task and struggle to different output at times. Thank you.
Yeah, no, that's a great question. So there are a couple of different approaches there. So one would be to kind of limit the amount of invocations it would do and the amount of times it would re-reason or produce that that process for thinking. So whether it's using the React framework on the back end of kind of chain of thought, controlling how many times it can produce that before it would say fail, and then trigger some sort of a complete retry mechanism or fallback mechanism. So that's kind of one approach that you would go with. And another way that you can kind of do that is to make sure that the different agents that are defined, the prompt engineering really communicates what specialization it has, and focusing on the prompt engineering piece to well define the agent and its capabilities, and being very specific with the instructions can definitely help in terms of preventing that endless loop of iteration in terms of who to kind of delegate tasks to and how to manage those as well. So there are a couple of different techniques that can be employed for that piece.
How easy is it to go back and figure out if something is going wrong with the output? Where in the process?
Yeah, no, that's a great question as well. So one technique that I like to use, and this comes in handy when you're developing these systems and debugging as well, is making sure that those large language models are being verbose. So it's printing out its different thought processes, the results of each tasks, the results and the outputs from calling these certain actions and tools as well. And that way you're kind of able to keep track of where something went wrong. Another technique you can use is adding tasks in between different steps for validation. So if you have an expected output or an expected format from maybe a sequential process, that way you can keep track of what the point of failure is and where you might need to go back and do a little bit of reworking.
I'm just wondering, it's great, thank you very much for this great talk. I'm thinking about how you move from this theoretical concept, right, of agents to the actual game. How you put this together with the game engine. You take for any Unity or Unreal. How would you move from this to the game itself?
Which one of you?
There's a few ways. I think as conceived, this is more of a back studio use, right? So it's for folks while you're developing the game, to inspire themselves to find sort of new avenues. If you wanted to put this directly in the game, the challenge you run into is how do you communicate game state, how do you construct prompts and all that. There are a few, there's Onyx, for example. I think there are ways to structure this, but it's very custom per game. And I think it'd be really interesting for game engines to include sort of standardized functionality on that. Not hard standards, but recommendations on how to do this well. I think that's a field of growth. Maybe we'll talk about that in the Future of AI panel. But there's been some interesting work in academia on describing video games to AI in a general level. I think it's called Video Game Description Language for Artificial General Intelligence for Video Games. It's a long acronym. But I think it's an open body of work. Each game is solving that separately on its own for the moment. But as an industry, I think we'll kind of coalesce around standard-ish solutions.
Yeah, I think that this is very important because it's a practical step, right? I myself, in summer, presented a work at SIGRA for for this small game, right? When you interact with the agent, but you need to train, for example, in Unity, for example, if your agent will be able to perform actions, you need to train that agent, right? Using machine learning, some machine learning techniques, and then you need to fit with the language model. In this case, it was a small language model, right? And you need to build a pipeline, right? So, for me, at this point, it's difficult just to see how we connect all these agents inside of the game, some specific game engine. So there should be, the game engine in the future should be able to allow this, right?
Sure.
To move from this.
I will just add to Sergio, we have 3 minutes. Did you want to switch room to go to the other room for another presentation? Please, thanks again.
Thank you.